Hello, everyone, and welcome to Chapter 7 of Chemical Structure and Reactivity. It's a pleasure to have you all here for those in Discord, and also for those watching online. So if you are watching this, I'd like to give my heartfelt thanks to you for helping support the CODS YouTube channel. This by me, and right here we have the shoutout list. So honestly, you can just leave a comment on the YouTube video, or you can just talk to me so even you could get on the shoutout list. So, this chapter will mainly talk about thermodynamics and equilibrium. And when I read this chapter, honestly, I loved how it went in depth with these concepts. And if you compare it to other textbooks like Zumdahl's, Zumdahl seems like surface level, like just skimming the surface, while this chapter just kind of drills a hole into the earth and calls that their approach. That's what I mainly like about this chapter. So, here's an overview of this chapter. You don't need to memorize all of this right now. We're just going to do an introduction to thermodynamics and state functions, and then we're going to talk about entropy and some more state functions like internal energy and enthalpy. And we will also talk about Gibbs free energies and the second law of thermodynamics. And then we'll mainly just talk about equilibrium in both its basic definition and how it can relate back to thermodynamics. So, we'll talk about what thermodynamics actually talks about. So, this is more of a shift from the microscopic world to bulk matter, which means in the words of Kurovax, right? I've seen his lecture. You don't need to know anything about the actual chemical reactions. You just need the general laws. And overall, thermodynamics is just a beautifully constructed field. In fact, I saw this quote from Albert Einstein in the chapter, right? He said that classical thermodynamics, which is what we're talking about, will never be overthrown. So that really shows how well constructed it is, especially from a guy who overthrew classical mechanics in favor of quantum mechanics. Let's go. So, first I want to talk about spontaneous processes. So, this is an experiment that I don't want you to do at home, but it's still useful for understanding the concept of spontaneity. So, copper. Copper is a nicely conductive metal, and if you can obtain a piece of it, and you have nitric acid in a flask while having personal protective equipment and doing this reaction under a fume hood, you will create a chemical reaction that produces nitric oxide or nitrogen monoxide, which then quickly turns into toxic nitrogen dioxide until completion. So it violently reacts. So basically, when chemists say that a reaction is spontaneous, it will keep going once the right conditions are met for that reaction to occur. Like, for example, dropping sodium in water. I'm pretty sure we've all seen those now red videos or those experimental chemistry videos where they get some kind of alkali metal like lithium, sodium, potassium and drop it in water, and you can see this violent reaction occur. So that's another example of a spontaneous process. And in addition, chemical reactions can end up at equilibrium, which is basically where if a reaction is reversible, then there will be some point known as the equilibrium point where the rates of the forward and reverse reactions are possible. I'll explain that later. And this equilibrium relationship can be expressed by the equilibrium constant. I want to talk about a common misconception of a process being spontaneous. Right? So, what many people think is that there's some kind of direct relation with the reaction being exothermic. So basically, exothermic, that means the reaction releases heat into the surrounding environment. So some people may think that there's a direct kind of connection between the reaction being exothermic and spontaneous. Now, this is wrong. So let's take this example right here. We have the toxic gas, nitrogen dioxide, as I said in the last slide. See, at certain pressures, it can spontaneously react to form dinitrogen tetroxide. And if you put this high pressure dinitrogen tetroxide and subject it to a lower pressure, this endothermic process will occur spontaneously. So that's a common misconception. We can use this kind of equilibrium to describe how both Exothermic and endothermic reactions can be spontaneous. So the forward dimerization of nitrogen dioxide is exothermic, while the reverse reaction is endothermic. So right here was just that explanation that I talked about in the image, and we'll go on to the next slide. So next we're just going to take a short detour onto the world's state functions. So before we talk about entropy, we need to go over the concept of state function in two definitions. Onto like two personal definitions. So there's that kind of easy route. So a state function only relies on the start and end point of a process, not the path it took from start point to get to the end point. Now, this is chemical structure and reactivity right here, so the authors wouldn't leave us with that definition. So, to actually gain an in-depth understanding of state functions, properties of matter such as density only depend on how something is at the end of a process, not exactly how they get there. And the state of matter can be defined by variables such as pressure or temperature. And it's important to record the values of the state function to be used later, because that's the whole definition. It only relies on that start and end state. So one example of state function is the enthalpy of a reaction, or delta H. And here's the disclaimer for enthalpy, or like Gibbs free energy. When it is in kilojoules per mole, that is the enthalpy for the reaction in whole number coefficients. So you can see this kind of example of enthalpy reaction. So the first reaction, this is just combustion of hydrogen gas. These are not whole number coefficients, so that would not be the correct enthalpy. But if you times the entire reaction by 2, you get these whole number coefficients. So negative 484, which is 2 times the original enthalpy, that would be the enthalpy of reaction. I'll go on to the next slide. Next, we're just going to go over an introduction to what entropy is. So when this chapter talks about entropy, we're also considering different viewpoints on what entropy is. And also for the second law of thermodynamics. So I already covered the concept of spontaneity. And the second law of thermodynamics says that for any spontaneous process, the overall entropy of the universe increases. So what we will do in the later sections is use our knowledge of what entropy is to see if that second law holds up. And I know this is kind of getting tiring, but in the words of our Lord and Savior Kurvax, thermodynamics, you don't need to know anything about the reactions themselves, just the general laws and equations. We're going to first go on to the microscopic view of entropy. So, you've probably been told before in like your physics, like high school physics textbook, maybe your high school chem teacher, that entropy is just an order of randomness, which kind of reveals some interesting problems, because that definition is kind of vague. So we're going to focus on mainly Ludwig Boltzmann's definition of entropy on a microscopic scale. So we're going to focus on what's known as energy levels. So back in chapter 2, you remember I talked about the concept of quantized energy levels for electrons and atoms. Now, not only can electrons have these quantized energy levels, but so can molecules. These energy levels are rotational, vibrational, and translational. And they're more closely spaced in energy compared to the electron's energy levels. So, for a system with n molecules and few energy levels, many distributions can be possible for a certain total energy. And the number of ways, I repeat, like the ways a distribution can be achieved, W, is equal to the factorial of n, and then the denominator, what that factorial of big N is going to be divided by, is basically all the populations of each energy level factorial just multiplied together. So, for example, take this C part in the image, right? If we take the C part, we can see that there are 14 total molecules, and there are 10 in the first energy level, and let's see, 1, 2, 3, 4. So in the energy levels 1, 2, 3, 4, there's only one molecule in there. The number of ways that this distribution can be achieved, W, would be equal to 14 factorial divided by 10 factorial times 1 factorial times 1 factorial times 1 factorial times 1 factorial. when we're talking about distributions and the number of ways a distribution can be achieved. The distribution of the largest number of ways that it can be achieved is shown in the Boltzmann distribution. And the population will obey this. And basically, it is found that the value of W for the most probable distribution is much larger than all other values of W. Which from that, if we have some kind of larger sample, we can assume that the molecules are always arranged in this distribution. If we want to determine the units for the entropy, which is the Boltzmann constant times the natural log of the maximum value of W, that natural log of W max will just be a number. So the entropy will be in the same units as the Boltzmann constant, which is joules over moles times Kelvin. Now we're going to talk about what changes can I make to a system, right? And how can that relate to entropy on that microscopic level? So, I kind of found this section a bit vague, but honestly, I think it's for good reason, because it said that to observe the effects of these changes, you will have to model the energy levels with quantum mechanics. Let's take, for example, some kind of sample, just like some number of molecules with some number of energy levels. So if you heat a sample, those molecules will be more evenly spread out throughout these energy levels, which increases the value of W. And since entropy is directly proportional to W using the formula, we can assume that the greater the temperature, the greater the entropy. And this checks out for the real world. Now, in addition, if you apply a constant increase in temperatures to systems, like, I don't know, 5 degrees Kelvin, and these systems are at different initial temperatures, then that change will be greater if the system is initially at a lower temperature. So if we have some system that's at like 1 degree Kelvin versus a system that's at 100 degrees Kelvin, if we apply a 5 Kelvin change, then that change in W or change in entropy for that matter, for the system that's initially at 1 degree Kelvin would be much larger. And in addition, increasing the volume of gaseous sample and increasing the molecular mass will make the gaps between energy levels lower, which leads to these molecules being more spread out across these energy levels. And in terms of entropy in relation to states of matter, liquids have greater amount of entropy than solids, and gases have a lot more entropy than liquids. So this Ni, right? That's basically just a population of molecules in some energy level. And with that energy level, we're just going to denote that I. And N0 is that initial population of molecules, which is basically just a population of molecules in that kind of first energy level. And that exp, that's just e to the power of this value. So in the denominator of this value, this is the Boltzmann constant times the absolute temperature in Kelvin. And negative EI, that's basically the negative of that energy level. So quite literally, the distribution with the largest number of ways follows this Boltzmann distribution. Now we're going to define what heat is. In daily life, heat can have like a vague definition, like your mom would tell you like, turn on the heater during the middle of winter, or cool this house down, the heat from outside is way too much. But in the world of thermodynamics, heat is defined as the energy that is transferred from a hot object to a cold object when they kind of touch. You can see in that image. And heat is not a property of matter, and therefore not a state function. Next, we're going to go on to what reversible processes are. So, in the world of thermodynamics, a reversible process is able to change direction based on an infinitely small change, or infinitesimally small change in some factor, such as in the transfer of heat. So in the transfer of heat, or just like the melting, boiling, freezing of just like anything, that is a reversible process. And if there's an infinitesimal change in some variable, then the change that results is also infinitesimal. Let's think about heat for a second. If there were a larger temperature difference, if we're talking about the transfer of heat, that would not be reversible, aka that infinitesimally small change would not affect it. So next I want to go over two important state functions of matter, which are denoted by delta U and delta H. So delta U is basically just the internal, I repeat, just the internal energy. And delta H stands for the change in enthalpy. Whenever you see delta or both lowercase and uppercase, that's going to represent a change in something. And so the internal energy is the sum of all heat and work, and the enthalpy is equal to the internal energy plus pressure times the change in volume. In certain conditions, these two quantities are related to heat. So during an isochoric process, the internal energy is equal to Q, which is heat, and during an isobaric process, same pressure, change in enthalpy will be equal to Q. So next, we're going to talk about entropy in relation to heat. So we already talked about entropy and Ludwig's Boltzmann's view on this, but this doesn't have to be defined concerning energy levels. So for any reversible process, the entropy change can be denoted as that infinitesimally small change in heat over the absolute temperature of the system. And here's something about heat, right? So the change in heat is equal to the heat capacity, which is the amount of energy in joules that's needed to raise the temperature of something by 1 unit. The reason why I'm not saying like 1 degree Celsius or 1 degree Kelvin is because heat capacities could be both. So I'm just going to do 1 unit instead to be a bit more broad. And remember, under isobaric conditions, the change in heat is equal to the change in enthalpy. And in addition, this delta T, that's the change in absolute temperature. The definition of entropy actually implies that, yeah, if heat is supplied to that system, then the entropy will increase. And the increase in entropy for a set amount of heat is larger if the temperature of the system is lower. Which is exactly that kind of point I made when I talked about entropy in relation to Ludwig Boltzmann's view. So now we're going to talk about how we can measure entropy with this past definition. So, the change in heat can be defined as delta Q equals CT times delta T. So the reason why I put CT is because heat capacity varies with temperature. So what the authors were trying to do in this section, they're trying to model heat capacity as a function of absolute temperature. Now, in addition, remember that under isobaric conditions, the change in heat is equal to the change in enthalpy. And the heat capacity will now be a constant pressure heat capacity. And we can substitute this into our previous definition of entropy if we're assuming isobaric conditions are present. Now, if we utilize this equation, then determining the entropy change will now be more graphical, which basically we can make a plot and determine entropy change. The entropy change between two temperatures is basically equal to a rectangle of height Cp in parentheses T over T and width delta T, as you can see on this graph. Between two temperatures, the total entropy change can be thought of as the sum of all those rectangles. And if we go back to our molecular view on entropy, we know that a perfect crystal has zero entropy due to there being only one microstate or just one way to achieve a distribution. So we can use our graphical method to determine that the entropy change between 0 degrees Kelvin and a temperature T, which is known as absolute entropy or third law entropy, because the third law states exactly what is said in the last point. So next we're going to go on to the second law. So I've gone over the different views on what entropy is, and I believe that you and I think, are in a good position to talk about the second law of thermodynamics. So here's a quick refresher. For any spontaneous process, the overall entropy of the universe increases. So I will divide the universe into two parts, the system and the surroundings. So quite literally, the system is just what we're analyzing, surrounding is everything else, and there's a boundary that separates these two. Now, the overall entropy change for the universe is equal to the entropy change of the system plus the entropy change of the surrounding. And the heat change are important for this section. So, if we use our definition of entropy in the two equations above, so our definition of entropy right here, if we use that definition of entropy and two equations above, I'm not going to go into all of the equation derivation, but basically, the entropy change of the universe is equal to the negative of the enthalpy change of the system divided by the temperature of the surroundings plus the entropy change of the system. Under isochoric, next we're going to talk about the second law of thermodynamics in relation to ice. Now ice, man, whenever I go to McDonald's, I always put ice in my drink. So let's start with a process, which is just turning liquid water into frozen water. Pretty simple, am I right? So, the first term for calculating the overall change of the universe, this negative enthalpy system over T surroundings, is positive because this process is exothermic, which means a negative enthalpy. Now, the second term, which is the entropy change of the system, is negative because, hear me out. So, if you freeze liquid water into solid state, those water molecules are going to get into more orderly states and release that kind of latent heat. Let's first try it with negative 20 degrees Celsius, which is below the freezing point of water. So if we plug these values into our equation, these values, we get a positive change in entropy of the universe. So that indicates that, yes, this process can happen. Now, if we just do, 1 degree Celsius, which is above that freezing point of water, you get a negative change in entropy for the entire universe, which means that no, you cannot freeze water at 1 degree Celsius. So next, we're going to go over Gibbs free energy. So Gibbs free energy is a statistic and is also a state function, and it basically just describes the spontaneity of a reaction, which is defined as the Gibbs free energy is equal to the enthalpy minus the absolute temperature times the entropy. So we can just expand that for a system with these delta values just to indicate change. So if we divide everything by T, we get this equation. So the negative of the change in Gibbs free energy, this is the Gibbs free energy equation. And if we divide everything by T, we yield the negative of the change in Gibbs free energy of a system over the absolute temperature is equal to the right part. If we go back to that equation, we can see that the right part of this equation is the exact same as the right part of this equation. So if we compare this equation to the last one, we can see that this left side, the negative of the change in Gibbs free energy of a system over the absolute temperature is equal to entropy change of the universe. So next we're going to go on to the most dreaded part of my US National Chemistry Olympiad tests, equilibrium. So the authors say that this part is the most important of the entire chapter, and that's because this section is a culmination of what we have learned so far. Anyways, let's start off with our first relationship. So the change in standard Gibbs free energy, so that's a new term, standard, is equal to the negative of the gas constant times the absolute temperature times the natural log of K, which K is just the equilibrium constant. If we talk about a reversible reaction, which is a reaction that can go in two ways, from products to reactants and reactants back to products, the equilibrium constant can be written as K equals the concentration of C to the power of C, concentration of D to the power of D, concentration of A. So that is how our equilibrium constant will be written. And disclaimer, only phases that will be introduced into this equilibrium constant are either gases or aqueous solution. And that's because their concentrations or pressures, which we'll talk about in a bit, can vary. Next, we're going to go over the equilibrium constant. So just more equilibrium constant. So For aqueous solutions, in the equilibrium constant, we use the concentration of these solutions for the values. So, generally, if we talk about the concentration, they're in big M, or molar. This is known as molarity, which is just moles over liters. However, I do know that in some textbooks, and especially in IB chemistry, they term it, instead of moles over liters, it's moles times dm to the power of -3. Remember when I said that the standard change in Gibbs free energy is equal to negative RT ln K? So what does that degree symbol mean? So that means that it is the standard change. And there's no kind of, in this table, there's no kind of definition for temperature, but generally the standard changes of state functions are measured at room temperature, which is 298 Kelvin. And so right here are just the standard state. Next, we're going to talk about how we can get the standard values of these state functions. If you can see with this chemical reaction, it's equal to this expression. Now I'm not gonna read all of that out. So while this example only has a change in standard Gibbs free energy, it can be replaced with any state function as long as you have the values for the formation. For elements in their natural forms, like H2 as hydrogen or O2 for oxygen, the enthalpy and entropy of formation is equal to 0. Generally, the enthalpy change for a reaction can be computed with a cycle where the reactions are broken down to elements in their reference state and then just rearranged back into the products. This is also known as Hess's law, which we will use later. So we're going to first talk about the standard change in enthalpy and standard change in entropy for reactions that have no ions. So, in a chemical reaction, bonds are broken and formed between atoms and molecules, which means that, of course, the standard change in enthalpy would be influenced. If a chemical reaction involves only breaking a bond, that's endothermic, because it takes energy to break that bond, right? And vice versa if a chemical reaction forms a bond only, because bonds include a lowering of energy. So, of course, we get some kind of energy that's just going to be released into the environment. Or bond dissociation enthalpies is the energy that's needed to break 1 mole of that bond between 2 atoms into its constituent atoms. Now, in terms of standard entropy changes in a reversible reaction, for an equation, chemical equation, the side of the equation with more moles of gas will have a higher entropy than the other side. And in addition, the formation of an ionic solid from gas phase ions will result in a significant lowering of entropy, because we're going to get a much more ordered state from that ionic solid formation. So next we're going to talk about the standard changes in enthalpy and entropy for reactions that have ions. So we're going to focus on standard change in enthalpy and entropy for hydration. Now, if we have some kind of ion, like if we dissolve an ionic solid in water, then that ion will have a favorable interaction with the water molecules, right? And thus we're going to get some kind of a change in energy. So, a simple model for describing the enthalpy of hydration at 298 Kelvin is given by this equation on screen. And as you can see, this equation will include the ionic radius in picometers. So that's something that you don't have to memorize, but I'd say it's useful to know. And this equation already predicts that the enthalpy of reaction is negative. It assumes that, in fact. And this is true, as forming a hydrated ion is always exothermic, because there's going to be that favorable interaction between the ion and the water molecules, right? Since the water molecules are polar. For entropies of hydration, 2 plus ions have a more negative standard entropy change than +1 or -1 ion. And as the ionic radius decreases, the change in standard entropy of hydrations becomes more negative. Right on, we're going to go on to the applications of thermodynamics. So this is going to be the first part. So we're going to first talk about the solubility of ionic salts in water. So we're going to utilize this reaction right here. And from this, we can think about Hess's law, which states that if a reaction has many steps, then the overall enthalpy is the sum of all changes that occur. If we utilize Hess's law, we can construct that standard Gibbs free energy change, which describes if a reaction goes on its own or not. And we're going to apply this to two salts, lithium fluoride and sodium chloride. So the standard Gibbs free energy for sodium chloride dissolving is negative, showing that it can fully dissolve in water, while it's positive for lithium fluoride, showing that it can't be as soluble as sodium chloride. And next, we're going to apply thermodynamics to the strengths of certain acids. So we're going to construct another Hess's law cycle in order to determine whether or not an acid will dissociate in water to some extent. So if we use Hess's law on hydrofluoric acid and hydrochloric acid, the overall standard Gibbs free energy change will be positive for hydrofluoric acid as negative for hydrochloric acid, which means that's way more acidic than hydrofluoric acid. So that's something neat to know with thermodynamics. We're going to now talk about acid-base equilibrium, aka the bane of my existence. Not Le Chatelier's. So, the definitions of what an acid and base do vary, but for now, we're just going to say that an acid will donate protons in solution, while a base will accept protons. And when an acid is dissolved in water, the hydronium ion, H3O plus, is formed, and when a base is dissolved in water, since it takes away a proton, and charges must be balanced, the hydroxide ion is formed. So then we get two equilibrium constants, Ka and Kb. So quite literally, these are just the equilibrium constant for acids and bases, if we look at their chemical reactions. So these are just going to be for a generic acid or a generic base. Now, next we're just going to talk about the autoionization of water. So, basically, water can act as both an acid and a base, making it amphoteric. And the autoionization constant of water from the chemical equation of it ionizing itself will be the concentration of OH minus times the concentration of H3O plus. And in addition, if we talk about acids, pKa is a useful way to look at the acid equilibrium constants, and this equal to the negative log base 10 of Ka. And this means that the lower the pKa, the stronger an acid is. So in addition, Ka times Kb is equal to Kw, which is that autoionization constant of water, for an acid slash base and its conjugate. So a conjugate base will just be an acid with that lost a proton, and a conjugate acid would just be a base that accepted a proton. So generally, the stronger an acid slash base, the weaker the conjugate will be. And we're just going to go over pH. pH is just calculated as the negative log of the concentration of hydronium ions, or pKw, which is the negative log of the autoionization constant of water, plus the log base 10 of hydroxide ions. So last, we're just going to talk about the amount of product at equilibrium. So let's first introduce a simple equilibrium, right? Diatomic A2 dissociates into 2 atoms of A. So the equilibrium constant here is expressed as the partial pressure of just A squared over the partial pressure of diatomic A times the standard pressure of 1 bar. So we can use something known as the dissociation constant, which is just a fraction of the reactant that will dissociate until we reach that equilibrium point. I'm not just going to go into this too deeply, but utilizing the partial pressures as in the table, we can now construct this equilibrium constant as this monstrosity. And we use the ideal gas law, we can also derive what the pressure is for the equilibrium constant and then substitute that into the equation. So now we have this monstrosity for the equilibrium constant. However, if we can assume that the smaller degrees of dissociation are present, we can just approximate in our derivation of this equation to 1. Now the value for the equilibrium constant isn't so bad. And if we rearrange that, we can yield that degree of dissociation more simply. So, increasing the equilibrium pressure will also decrease the degree of dissociation. And this is because if we increase that equilibrium pressure, we can approximate it to equal nRT over V, which is more simple. Which means that we can further simplify the value for the degree of dissociation. So, for a general case, if we cannot assume that a degree of dissociation is small, we can just solve this equation right here as a quadratic equation with this right side denoted by f. So next we can treat this monstrosity as a quadratic equation, and we can use this value on the right to solve for the degree of dissociation. So that's just it, honestly. So right here, that's the end. And in the words of probably the smartest man in the server, thermodynamics is abstract, but describes not so abstract processes. And right here is going to be your sneak peek for the next chapter. We're going to talk about trends in bonding, such as electron configurations and blocks, such as S block, P block, D block, and F block. And then we're going to talk about ionization energy, electron affinities, oxidation states, and just bonding across the periodic